Hi everyone. Today we're going to be solving some optimization problems. Optimization comes from the word optimize, so we're going to be looking for best or most efficient solutions today. I'll show you some examples and then we'll write a general procedure for how to go about these problems. So our first question here is, two numbers sum to 30, maximize their product. Okay, so when we see a problem like this, we hone in on the word maximize, right? That's what it's telling us to do, to maximize it. And we've seen in the past different maximization problems, maybe not written like this, but something like find the maximum of this function, find the minimum of this function. And when we've been doing that, we've been using the first derivative test. And today, what we'll do is we'll add some more context in real-world applications, but still finding max and mins just like we did before. So, two numbers sum to 30. Let's turn that into an equation. If my two numbers are x and y, then their sum has to be 30. So that means x plus y had better be equal to 30. Great. The other thing I need to do is maximize their product. So I should write an expression for their product. Product, of course, meaning multiplication. So x times y is the product, and maybe I'll call that p for product. Great. And now here's the trouble. You'll notice that we have two different variables. Anytime you have two variables, equations can be very complicated to solve. So what we'll do is, just like what we did in Algebra 2 when you were solving systems of equations, we're going to solve for one variable in terms of the other one, and then substitute that into the second equation. This way we'll create an equation with just one variable. If I look at this equation here, I can simply move the x to the other side to solve for y, and this tells me that y is 30 minus x. Okay. Next, I can plug that into my product here, and I'll have x times 30 minus x is equal to p. And this is the function that we want to maximize. So let's maximize it. To do that, you'll recall that we take the derivative. Now, the maximum of a function can occur when the derivative is equal to 0, right? Because the slope of the tangent line is 0. And it's important that we test that this happens when the derivative is changing sign from positive to negative. Because the derivative could also be 0 at a minimum. And we want to find the maximum here, so finding the minimum won't be too helpful. So let's do that here. We have our product equation, which is x times 30 minus x. Okay. And I'll just distribute my x's here, so p is 30x minus x squared. And then what I'll do is I'll take the derivative here. So dp dx is equal to 30 minus 2x. And again, we're going to be setting this equal to 0 because local maxima happen when derivative 0, slope of the tangent line is 0. Solving this for x gives me x is 15. Now I have to do a quick check to make sure that this 15 is a maximum and not a minimum. So I'll draw my sign line here. There's a 15. If I pick any number less than 15, plug it into my derivative, I'll find that my derivative is going to be positive. Yep, any number you like less than 15, maybe 0. 30 minus 0 is 30. Great, so it's positive. Any number bigger than 15, maybe like 10 million. 30 minus 20 million is going to be negative. Any number bigger than 15 is going to be negative. So indeed, I find that at 15, my derivative is changing from positive to negative, which means that 15 can be a local maximum. And now, the only thing left, we've found x. We still need to find y. So fortunately, we have this nice equation for y. Y is 30 minus x, so that means y is also going to be 15. So in this case, if two numbers sum to 30, and I want to maximize their product, both numbers have to be 15. The maximum product can be 225. So that's a basic optimization problem. We're given a few things to work through. We have to write those things as equations, and then to maximize it, we'll take the derivative, set that derivative to 0, and then make sure that it changes from positive to negative at that case. I'll put up another example here. This second example is going to be a little bit more involved and still just purely math. And then after this next example, we'll jump into some more real-world context examples. So you can follow along with this problem if you'd like. It's number 6 in your textbook in the optimization section. Basically, it says this. I have a function, and that function is y equals 12 minus x squared. Okay, here's my function. And I'm going to draw a rectangle, but I'm going to give you some specifications on this rectangle. This rectangle has its base on the x-axis. Its vertices on the parabola, and I want this rectangle to be have its maximum area. So I'm going to draw a rectangle with the base on the x-axis, vertices on this parabola. Great. And then I want to maximize its area. Okay. Whew. So whenever I'm given a prompt like this, anytime it's draw or there's a shape or something involved, I always want to draw it. That's my first step. Drawing it will give me a nice visual on what's happening here. So I'm going to draw this starting with 12 minus x squared. We can draw 12 minus x squared just like this. It's a nice parabola. The negative means it's reflected over the x-axis, so it opens down. The 12 means it's shifted up 12. So here's my picture. And now my rectangle, well, the base of the rectangle has to be here along the x-axis, and the vertices have to be actually on the parabola. So here are some vertices, and here's my rectangle. Perfect. So my goal is to maximize the area of this rectangle. Now this is going to be a little bit tricky because I don't have any equations yet other than this equation, and it doesn't immediately seem obvious how this parabola is going to factor into our area equation. But since it's asking for area, I know the area of a rectangle is length times width, so let's figure out what the length and width are. Thanks to the nice symmetry of a parabola, where this particular parabola has its axis of symmetry right on the y-axis, I can figure out that if I go some amount here, it'll be the same amount that I go over here. These will both be the same. So let me pick my favorite x-coordinate. Maybe I'll call this guy b. Okay. And then this guy would have to be negative b. Great. So then the last question is, well, I can figure out the length of the base here. From negative b to b, that's just 2b units long. But can I figure out the height? Well, thankfully, I know the coordinates of this point because I know the x-coordinate is b. So I can plug that into my parabola equation and figure out that the y-coordinate of this point is 12 minus b squared. Since the y-coordinate of this point is 0, the height here is actually 12 minus b squared. So now I'm in place to find the area of this rectangle. As we recall, the area is length times width, or base times height, however you like to say it. So our area equation is going to be 2b, which is the base, times 12 minus b squared. And this is what I need to maximize. But again, I know how to maximize this. I'll just do the same procedure as last time. I'll take the derivative, I'll set that derivative to 0, and I'll make sure that that derivative is changing from positive to negative at the particular point that I find. So let's do that here. Right. We have our a right here. I'm just going to distribute this, and I'll get 24b minus b cubed, 2b cubed. To solve for b then, first I need to take the derivative, set that derivative 0. So dA dB is going to be 24 minus 6b squared. And I'll set this to 0. And now I want to solve for b, so I'll move the 24 over. Negative 6b squared is equal to negative 24. I'll divide by negative 6, so b squared is 4. And I'll take the square root of both sides, and I'll get b is plus or minus 2. Now, the way that we defined our b is that it represents our x-coordinate here. So plus 2 is actually going to be the same as minus 2, because if I define b to be negative 2, then negative b would be positive 2, and vice versa. But let's just check with our sign line here. Make sure that this positive 2 is going to be a maximum here. I'll plot my negative 2 and my positive 2. And what I'll do is I'll pick numbers in all of these regions and see what happens. So let's pick the number 0. If b is 0, the derivative of the area is 24. That means this is positive in this region. If b is larger than 2, say b is 10, then this is 24 minus 600, which is definitely negative. Similarly, if b is something like negative 100, this would also be negative over here. So this is the point that I really care about here. The derivative is going from positive to negative, so that means that we have to have a maximum when b equals 2. So I definitely want b to be equal to 2 here. That's going to be our maximum. Now, if I want to know the dimensions of this rectangle, I can just take this and plug it in to our base and to our height. So the base has to be 4 units long. The height has to be 8 units long. So the area, the maximum area, is 32 square units. Great. So again, with both equations here, I've done the same thing. Every time it's asked me to maximize something, I have to turn the words into equations, because equations we can maximize for days. We've been maximizing them for the past few months, and so it still should take a bit of time, but shouldn't be terribly difficult once we get the hang of it. So here's our final example for today. It's more of a real-world example here. What we're going to do is we're going to say, all right, we have, you just went out and bought 200 feet of fence. Now, why would you do this? Maybe you are fencing off a particular area of your yard, right? You just got a new puppy. You want that puppy to be able to run around in your yard, but you need some of it to be fenced in so that the puppy doesn't accidentally run away. So you're going to build a rectangular pen in your yard using this 200 feet of fence. So using the fence, you want to build a rectangular pen in your yard for your new puppy. Sounds great. Ideally, you want your puppy to have the most room to run around in. You don't, for instance, want to make it maybe 200 by 1 foot. The puppy can't really run around so much in there. So instead, our goal should be maximizing the area of this pen. That's our goal, maximize the area of this pen. Okay, great. So again, it's not immediately obvious what equations we should be using here. The only number we have is this 200 feet of fence, and the shape that we have is a rectangle. So again, I'm going to start by drawing a picture. There's my rectangle. Everyone loves it? Great. I know that in total, I have 200 feet of fence. If I call this the width and this the length, Then all the way around this rectangle is going to be 200. That means that the perimeter, which is 2w plus 2l, should be equal to 200. And I'm asked to maximize the area. So this has to be my final equation. The area, as we know, is length times width. So again, I'm going to follow the same procedure. I have two variables, but I have two equations. So I can solve one of the equations for one of the variables, plug it into the other equation, and then use that to maximize this area. So what I'll do is I'll solve this equation, and it doesn't matter which variable you solve for. I'll just solve it for L. To solve it for L, divide everything by 2, so W plus L is 100, and then L is 100 minus W. Great. And then I'll go ahead and stick that in there. So now it's time to maximize our area. I know that the area is now W times 100 minus W. Well, that means that the area is 100W minus W squared. Okay. Again, to maximize, take the derivative, set that derivative to 0, confirm that the derivative changes from positive to negative at that point. So the derivative of the area is going to be 100 minus 2w. Set that to 0. That means w should be 50. Let's confirm that at 50, we're changing from positive to negative with respect to the derivative. So if I plug in a number smaller than 50, 100 minus twice that number is going to be positive. A number bigger than 50, that's going to be negative. Great! So that means when the width is 50, I'm definitely changing from positive to negative. So that means I'm definitely at a maximum value. The final thing would just be, what's the length? Great! So my length is 100 minus w. If my width is 50 feet, then my length, turns out, is also 50 feet, and my area should be 2,500 square feet.